Our very last section is 10.4. It's Taylor series approximations. We're going to end on a high note here. What's this all about? It's not a very long section, but an interesting one. So the nth degree Taylor polynomial, we learned that back in 10.4, approximates our function f of x, right? So what can we do with this? Well, if our nth degree Taylor polynomial approximates f of x, then we know there's some kind of an error involved. That's what we're looking at here. Okay, so I'll say f of x is approximately equal to the nth degree Taylor polynomial. Okay. The remainder, sometimes referred to as the error, we say is capital R sub n of x. So that's the nth degree remainder for the Taylor polynomial. Here's what we know. Whatever that remainder, and by the way, we always think of remainder as positive. It's like a distance, like an error. Error is always thought of as being a positive. So the absolute value of the error, well, wouldn't that be the difference between the original function when you evaluated x and the nth degree Taylor polynomial when you evaluated x? So if you take that difference, that's going to be the error, right? Okay. Here's Taylor's, so this is kind of like, you don't really need a whole lot of deep thinking to get to here, but you definitely do when you get to Taylor's inequality. So Taylor realized this, of course, and he developed this way of finding the maximum possible error, so you'll know how close you are in your Taylor polynomial to the real value, even though the actual function value in his day would be unknown. Here it is. Kind of intimidating at first, but let's read through it and maybe it won't be so scary when we're done. Okay, so there's your nth degree Taylor remainder and the absolute value, right? It's less than because we won't know the actual function value in theory, right? We're approximating with this for a reason. So we don't know what the actual number is. If we knew what the actual number was, we wouldn't bother with the Taylor polynomial. We'd just use that. So we want to get a maximum estimate for the error. How far are we off, right? Here's how it goes. What's in here, it should look very familiar. That is the nth term for the Taylor polynomial, but one more. So it's the n plus 1th term, right? In the Taylor polynomial, it was the nth derivative of f over n factorial x to the n. Well, here, instead of all the n's, we have n plus 1. So it's the n plus 1th derivative of f, n plus 1 factorial, x raised to the n plus 1. Now, something you notice is that we are evaluating at t. So what is the deal with this t? Let's talk about that. Where t is a number somewhere between 0 and x, okay, where we center all of these at 0. So t is somewhere between where we're centering and the x value. And it maximizes that n plus 1th derivative of your function. Maximizes the absolute value, I should say. Okay. Now this thing about t is kind of strange. Let's do a problem. Maybe it will be less intimidating then. Okay. Consider the natural log of 1.7. Now, in our day, right, we can just put that into a calculator and get a very high degree of accuracy. If we wanted more accuracy, we maybe could use a computer or something else. But, in Taylor's day, they couldn't do that, right? So they needed a pretty sophisticated way of approximating these things. Actually, truth is, we haven't even gotten much further than that, because we say, well, I'll grab my calculator. What's your calculator doing? Your calculator is using a Taylor polynomial to calculate this sort of stuff. And it's doing it to very high accuracy. It has very little error. We're going to get some insight into what that process is like. Okay, so consider the natural log of 1.7. Part A, we're going to approximate this value using the third degree Taylor polynomial. We're going to use that basic Taylor series back from 10.3, the natural log of 1 plus x. And we're going to approximate that to 6 decimal places. Okay, so let's start by thinking back to what that basic Taylor series was from the 10.3 notes. It was this, right? The natural log of 1 plus x, it was, if you think of the infinite series, it's equal to x minus 1/2 x squared plus 1/3 x to the third minus, if you kept going with the pattern, it would be minus 1/4 x to the fourth plus dot, dot, dot. It keeps going. We don't need to write the nth term when we do these sort of questions. We just need to write out, and I would advise go maybe one or two beyond what they list. So, you know, if you see that pattern, 1/2, 1/3, 1/4, it's also alternating, positive, negative, positive, negative. Let's write one more. You could write two more. Okay, what do I have in brackets underneath here? We're going to approximate this, the natural log 1.7, using P3. This is awesome. They've already done the work for us. P3 of x is right there, the third degree. We don't have to find that Taylor polynomial ourselves. We'll just use the one they already have given to us. Stop at x to the third. That's the third degree Taylor polynomial. And just to give you some insight into the remainder, all of the terms that are left are what make the error. They give the remainder after P3. So that's the third degree remainder for that Taylor polynomial. Okay, so let's pick it up. Let's use this right here on to the next page. So there's P3. Again, we just took that right out of what they told us that basic Taylor series was for natural log 1 plus x. Think back, okay, they're asking us to approximate the natural log of 1.7, and we're using the natural log of 1 plus x. So what value of x should we plug in? And well, if it's 1 plus x, then x equals 0.7, right? Plug in 0.7, we get that. 0.7 is what we want to plug into there, and this is going to do it for us. Plugging in 0.7, 0.7, P3 of 0.7 equals 0.7 minus 1/2, 0.7 squared, plus 1/3, 0.7 to the third. Punch all that in. We were supposed to round this to 6 decimal places, and it will be 0.569333. I believe the threes just keep repeating, so we'll stop at 6 decimal places. Okay, that's really great. That gets us the third degree approximation for natural log 1.7. Pretty darn accurate, 6 decimal places. Nothing to sneeze at. And of course, we want to find remainder, right? That's what this section is all about. Find the absolute value for the remainder of that third degree polynomial. Okay, so here's where we will use Taylor's inequality. Here's how we get started. We know in the formula that n equals 3, R3 of x. So we're going to put a 3 in every place that n appears, and it's always adding 1. So there's 3 plus 1. It'll end up being the fourth derivative. N plus 1 factorial means 4 factorial. and x raised to the n plus 1 is x to the fourth. All right, again, so far so good. Again, we know we're going to plug in x equals 0.7. All right, 0.7, 0.7. So we've got most of this figured out. The one part we don't have figured out is that numerator. Because it doesn't have x, it's got t. And what's up with the t? So let's look further into that. What is the value? What is the fourth derivative of your function at t? And there was those conditions on t. First, let's find the fourth derivative. Well, what is f of t, you ask? So it's the same function, natural log, that we use for the basic Taylor series, natural log 1 plus x. But we think of it as having the variable t. Okay, so the reason why they use the variable t is simply not to confuse. We are already using the variable x here. This needs to be a different variable, and so somebody said, let's use t. I don't think it's because it's a Taylor series. I think t is just another common letter, a variable letter to use. All right, so we need, to begin, we need the fourth derivative of that. All right, well, it's going to take a little bit of work. So the first derivative, simply 1 over 1 plus t. But think of it like this, 1 plus t to the negative 1. That will make it much easier to take a second derivative. Okay, so the second derivative, no big deal, multiply the negative 1 down, it drops to a negative 2. Even if you were to think of the chain rule, the derivative of the inside is just 1. So times 1, we don't need to write that. Let's leave it like this so we can take a third derivative. Well, a third derivative, multiply the negative 2 down. It drops to a negative 3. Again, the chain rule would say multiply by 1. No big deal. We need to do this one more time. The fourth derivative, multiply that negative 3 down, drop it to a negative 4. Chain rule, multiply by 1. Negative 6, quantity 1 plus t to the negative 4. All right, now I advise rewrite it like the fraction, negative 6 over 1 plus t to the fourth power. And we've got our fourth derivative there. Now the question of the t. Oh, it looks like I'm doing that on the next page. Okay, so here's what it said back in Taylor's theorem. It said use the value of t, and t is somewhere between 0 and x, that maximizes that fourth derivative. So what t value for t between 0 and 0.7 will maximize the absolute value, that's important, of the fourth derivative, negative 6 over 1 plus t to the fourth. Which value of t in here should we plug in to make this whole thing as big as possible? Okay, so we don't need any fancy techniques for this. We're not going to take any derivatives or anything like that. Just think about it. What value of t in here should we plug in to make this as big as possible? And it's pretty common for it to be one of the two extremes. Okay. Should we pick t to be 0? Would that maximize this whole thing? Or should we pick t to be 0.7? If we plugged in 0.7, would that maximize this whole thing? If you're not sure, grab your calculator and just test the two extremes. And so for us, well, let's see. Again, there's an absolute value involved. So negative 6 divided by, hey, if I pick 0, 1 plus 0 to the fourth, what's that going to give me? Negative 6. So if I pick t equals 0, then I take the absolute value and I get positive 6, right? What if I picked the 0.7? What's that going to give me? Negative 6 over 1 plus 0.7 to the fourth. Oh, I multiplied there. Wow. My mistake. I meant to say negative 6 divided by 1 plus 0.7 to the fourth. Okay, an absolute value, 0.72 or so. Well, clearly the bigger one is 0. And maybe some of you saw that, without plugging the numbers in. But yeah, if we put in 0 there, then the denominator is as small as possible, and that makes this as big as possible. So in this case, pick t equals 0. Plugging that in will give you 6. Okay, that is the most difficult part of the problem. Now we're ready to go. Put it all in. That numerator becomes 6. It's the third degree remainder. Absolute value less than all this. Okay, 6 over 4 factorial x to the fourth. Remember, our x value we can now plug in is 0.7. And here I've got the answer. R3 of 0.7 is less than 6 over 4 factorial, 0.7 to the fourth, and you should get this number when you're done. Remember, 4 factorial, 4 times 3 times 2 times 1, that equals 24 here. So 6 over 24 times 0.7 to the fourth will give you that number right there. And there's the maximum error. The error might actually be less than this, but this is as big as the error can possibly be. Okay. We've got another example coming up in a moment.